Hi, everybody. Thank you for joining us today. Dr. Toni Sauncy will be giving a virtual colloquium titled Living the Life in the Physics World, Hard Work, Serious Skills, and Necessary Frivolous Diversions. She is a professor and the chair of the department at Texas Lutheran University and also the former SPS and Sigma Pi Sigma director. Thank you so much for joining us. Just a reminder, this talk is being recorded, so please be respectful in the chat with any questions you may ask. And Toni, when you want to get started.
All right. Thanks for all of you for spending a few minutes with me this afternoon. This is super weird because I cannot see your faces, and I am a, in your face kind of physics person, and so this is going to be weird. So I'm just going to tell you what I'm going to tell you, and then if you have questions, please feel free to interrupt me at any time because then that feedback is really good for me. So I'm going to just tell you a little bit today about my story because I always like to hear everybody's story, and so I thought maybe you would like to hear a little bit about mine. And then hopefully we'll have time to get to some more serious stuff like how you're going to get a job and also some physics. Can't have a physics talk without physics. Before I start, I wanted to just stop for one moment and say that I am very concerned about what's going on in the world right now. In my world, Black Lives Matter, and I understand that I will never understand why or what it is to be in the shoes of my Black students and my Black colleagues, but I know that I am committed to doing my part to try to change the world in whatever way that I can. And I think all of us who have privilege should be responsible for changing the world in our own spheres of influence. So I just wanted to take this opportunity to say that. It's important to me, and I know that it's important to many of my colleagues in the physics community. So here's what I'm going to talk about today. Three things: hard work, serious skills, and then necessary and frivolous diversions, which you might have guessed already has something to do with bubbles, which I love. So I can't start off without some physics. Here's a little physics path integral, and I'm going to talk a little bit about my path. So hopefully you won't get too bored about this. So hard work. I like to say that I'm an accidental physicist. I started school right after I got out of high school, and then I dropped out and I went back later so that I could be a math professor or a math teacher in high school. And I couldn't finish my math degree at the community college, so I started driving, literally driving 2 hours each way to go to school to Texas Tech University to finish my bachelor's degree so that I could teach high school math. And then my friend who I was driving with decided he wanted to be a physics minor, and I said, okay, whatever, and I did that. So it was accidental that I even got in physics in the first place. It was really just for convenience. I took modern physics along the way, of course, as for my minor, and then I was met with my first challenge, and the challenge was you could either do a lab that accompanied the modern physics, or you could do a research paper in the modern physics class. And I said I wanted to do the lab, and I had an instructor tell me that was not a good idea because women are not really very good in the lab. And I didn't take that very well, and so I took the lab. And I can say without any doubt that I am an experimental physicist, and I did quite well in the lab. So that was my first sort of stumbling block. And then I had a serendipitous opportunity to take a classical mechanics class, which was not part of my minor, but needed people to make the class. And it was the second half. I hadn't had the first half, but that's when I met my very first female mentor in physics, and her name is Shubhra Gangokadiye, and she is shown here on my slide. She is just still an inspiration to me and a prolific researcher, and the first person to get me interested in materials science and semiconductor physics. And so then I had my next sort of accidental thing. I decided I would take an optics class where I met my second mentor to be my advisor. And it was there really in the dark of that lab that I fell in love with physics. I was fascinated by anything that had to do with light and materials that interacted with light. And so that's really sort of how I got to be a physicist. I was invited then to join the graduate school, the graduate program there in physics, and I did. And then I had an interaction called the qualifying exam. So if you do go to graduate school and you do decide you're going to get a PhD, then most departments, and not all nowadays, but many have the qualifying exams, and many of you may have heard of these things. But for me, the experience was pretty awful. I studied for a long time. I thought I knew physics, and then every single day I went into the qualifying exam with my pencil because that's what you could take with you. It was clear to me that I didn't know anything, and I went home crying every day. So I ended up at the end of my qualifying exam having to take the oral part of the qualifying exam. So I was already terrified, and I went through about probably 45 minutes of questioning about anything that they wanted to ask you. There were a number of questions that I thought I did pretty well on, and then one professor looked up at me and he said, "Okay, why does a bubble turn dark just before it pops?" And I stopped, and I you know, I really had never thought of this, and I'd just been doing Hamiltonians and Lagrangians, and so I went to the board and I started putting things on the board about film thicknesses, and it took me about 15 minutes, and then I turned around and he said, "Are you done?" And I said, "Yes, I'm done." And he said 2 words: destructive interference. So I felt very uneasy about that. I ended up passing the qualifier, but I was not sure why still. But the first thing I did was run home and blow a soap bubble and find out if that were really true, because I honestly had never noticed that, but it is true. And if you look at the soap bubble, just before it pops, beautiful colors will sort of go away and it looks this sort of dark gray color, and then it will pop. It's true. Please try this at home. I encourage it so you know it, so that if anyone ever asks you that question, you'll be ready, because I was not. So I survived. I had a great research experience. Of course, my research advisor was terrific. And then I started my first teaching job, and thought that I was going to make lots of PhD students, because that's what we do, right? Well, at some point in my career, probably about 8 years in, I had sort of an enlightenment. I really started thinking about what you do with a physics degree a pretty long time ago, but it wasn't really until I went to the SPS national office about 8 years ago and started working on this project, which was an NSF-funded research project to figure out what people do with a physics bachelor's degree and which departments around the country are doing a good job of putting people to work with their physics bachelor's degree. And so this project really caused me to pause and have a reality check and really have this shift from what we view as very valuable in the way we design our physics programs and the way we design our curriculum toward getting people into graduate school, to really sort of serving a broader swath of students to make sure that we're preparing students for lots of different career paths. So these are a few graphics here from the Careers Toolbox that I worked on. So we sort of just divided into 3 broad groups, and of course you could probably subdivide it, but we know that physics students can teach, we know that they might go to graduate school, and we know that they go into the workforce. And before I really started thinking about this, I just figured that most people go to graduate school because that's what we prepare students to do, right? That's what we want them to do, so we can put a feather in our cap and say, where our students went to graduate school and which one of our students got a PhD. And we hardly ever bragged about which student got a great job and which student is making great contributions to the workforce. And so for me, I think of this as really an enlightenment, because physics students have so much to offer the world in their unique preparation and their unique training. So I really changed the way I think about this. And so to me, as I look on the things that I've done in my career, I think that this service and this work that we did on the Careers Toolbox is really maybe one of the more important things that, that I've ever done. I want to just then talk a little bit about the Careers Toolbox and what's in there, and point out that all of these materials are free and they're online. If you just type in Careers Toolbox SPS, you'll get there, and all of these materials are online and free to you. Please use them. They work pretty well. So really, the thing that we have to think about when we think about our physics degree is knowing what we know, right? We have to know what we know. And that means we have to have some idea about how our knowledge and skill set fit in with the workforce and what people need in the workforce and so on. So one of the things that's in the Careers Toolbox is this planning and brainstorming to figure out what you know and how well you know it and what it means to the rest of the world. In doing that, you sometimes figure out that there's holes in your preparation, or there are things that you probably should know that you don't know, and so it's a really valuable exercise. So before we look at that exercise, I just want to show you this data, and this is, of course, available on the AIP website. This is from the Statistical Research Center. This is data that they collect from students who have graduated with a bachelor's degree in physics, and they go to work and then they hound them and find out, tell us more about what you're doing. And so these are some of the skill sets that students and then now employees report as being important as they are working in whatever job they get. Many of those jobs are in engineering. Some of those jobs are in computer science, mostly in some sort of technical workforce, and the data is similar for all of those jobs. I wanted to point out on this slide that up here at the very top is the ability to work on a team. And many people would kind of assume that that's a soft skill, and it is maybe a soft skill, but it's, to me, one of the, and obviously on the data shows it, it's one of the most important things that we can do in physics is have you working in groups, have you collaboratively working on projects, and so you're developing this ability to work with people that you may like and sometimes you might not like, but the work has to go on. You can see some of the other things that are on here, the hard skills that I would say, advanced math. It's used, but it's not nearly as important sometimes as things like working on a team and being able to write well. Sometimes students physics thinks that they don't have to learn how to write well, but in fact, because of the nature of the work that you do that's technical and complicated, it's maybe even more important for you to learn how to be a good writer. So anyway, this is a list of skills. This is included in the Careers Toolbox. You should take a look at it, because this is one of the places where you can look at your experience and say, oh, maybe I need to patch up a hole in my experience a little bit by participating in some activities or experiences. So the best way to figure out who you are in terms of your skills and knowledge is to take inventory. And we recommend that you do this. I recommend it to my students to do it at the end of every semester. You should constantly be asking yourself, what can I do right now that I couldn't do 3 months ago at the beginning of this class? Or what can I do right now that's different and better than it was before I started my summer internship? So this is the way that you're constantly keeping on top of how you're growing, how you're learning, what your repertoire of skills and knowledge are that you're gaining as you have these experiences. So the idea is that once you sort of get a handle on what you know and the knowledge that you have and the skill sets that you're developing, then you start to match those with real world needs, right? You may not be working in an optics lab, for the rest of your life, but there are skills that you learn in that optics lab that are going to pay off in any sort of technical job. So the idea is to help you, and as a mentor, this is my job, to help my students understand what you're learning now and how it connects to and transfers to jobs that you might have in the future. So this first exercise that I wanted to just talk quickly about today is called, it's a brainstorming, where you brainstorm all of your experiences and figure out what are the things that you are best at, what are the things that you have the most knowledge in, and what are the skill sets that you have based on this huge array of experiences that you might have had. So there's an exercise in the toolbox that you can do. It's a sort of a 4-part grid where you just sort of brainstorm, just brain dump everything that you've done in sort of categories, and then use those categories to kind of pick out and distill out things that you've had a lot of experience doing, and then maybe identify areas where you might just need to do a little bit more. So it's this knowledge and skills assessment that's going to form the basis for all of your job searching and all of your ability to land those special jobs that you want, because you're going to build a knowledge and skills based resume. So this is where it starts, and this is not something that you can do one time. You have to do this many times. As I said, I recommend you do it at the end of every semester, at least the end of every academic year. So then once you have this idea of what you know and who you are as a professional, then you need to start thinking about things like a resume. So once you've got your knowledge and skills down, you want to practice figuring out how do you put that on the resume. And that's going to require a few revisions. You're going to want to say it in a way that it's meaningful to the employer that you are trying to get a job with. And that means you're going to need to tweak your resume depending on what job it is you're looking for. So this is a tool in the toolbox. This is tool number 7. This is a huge resource. We've added a page of action words, which will help you write your resume with strong language that will allow you to appear to be, well, that will emphasize your strengths to a prospective employer. Also, there are 3 example resumes in the toolbox that give you an idea of the kinds of ways you can write your resume. You don't always have to put your GPA. Sometimes you want to put your GPA. It really just depends on, you know, what, oh, somebody just asked me a question. So in fact, if you look at Careers Toolbox, so the question was, what's the difference between a CV and a resume? So if I were you, I would be keeping both. So the CV, the curriculum vitae, is sort of cumulative record of everything that you've done that relates to academia, to your work, to your research. It's everything. So it's usually many pages. The resume is a distillation of that CV that's written for a particular job that you're trying to get. If you're going into academia, for example, you're applying for a graduate position or something like that, then it's important to sort of expand on your research experience, and it may go longer than a page. But a resume is really a distilled version, sort of an abridged version of what might be considered a CV, where a CV has everything on it. The resume is going to focus on the knowledge and skill sets that you have that are relevant to a particular position that you're interested in, right? So there is a pretty big difference for that. So hopefully that helps a little bit. In any case, the toolbox has tips on both, how to prepare both. And sadly, if you look at most of your faculty mentors, we're a lot better at giving advice about how to make a CV because that's what we've done. Most of us have never gotten a job with a bachelor's degree. And to me, that's why the work that we did on the Careers Toolbox is so valuable. It's valuable to me as a faculty mentor, and I know it's really valuable to students because your mentors do not have the experience of getting a job with a bachelor's degree, most of us. So anyway, please take a look at it. So that's also in the toolbox. There's the next thing I wanted to just point out, and of course there's 9 tools in here, and this is the last one. It's got a really good section on preparing for the interview, both a phone interview and an in-person interview. By the way, just so you know, the whole point of the resume when you're job hunting is to get an interview. The resume is not going to get you the job. The interview is going to get you the job, because that's where people probe more deeply about your knowledge and your skills and ask you to tell those personal stories that you've developed as a part of preparing your resume and doing your knowledge and skills assessment. So really the interview is key, but that resume is what's going to get you that interview. So definitely this is one of the better pieces, I think, in the Careers Toolbox. So I hope that you all will take a look at it. So I have a little bit of time left, I think, and I don't want to spend too long because I know I can't stay in front of a computer this long. So this is my third item for the day, and that is necessary and frivolous diversions. And I call it that because one of the things that keeps me out of bed every day is being curious, having fun. And sometimes things get kind of boring if you do the same thing over and over and over again. I mean, I've taught freshman physics for a long time, and so every year I have to think of new ways to be fun about Newton's laws, because honestly, they have not changed very much in several hundred years. So this is an example of one of the things that I think is a little bit frivolous, but it was really a lot of fun. We just did this in my advanced lab this spring, and I'm going to hopefully try to write this up as a class paper, because it's really pretty fun, and we had a lot of fun. So I think you have to be able to combine the advanced math that you learn as a physics student with your sort of childlike curiosity. And just thinking about that and tying it back to the knowledge and skills assessment, you cannot build knowledge and skills, and you can't put together a really good resume if you're not filling your life with experiences. You've got to do stuff. And for us, that means we've got to do some physics. So I'm going to just give you a quick example. So this is bubble physics. We return to a soap bubble, and this here on the left is a picture that I took out of one of my students' lab journals that sort of gives you an idea about this experiment. So this is a dish right here with a petri dish, and we're going to blow a bubble in it, and we've got to have some kind of a light source down here, and this cone is a piece of white paper described by the author in this paper that I mentioned here. And then the camera has to be suspended at some height above this bubble, and then we're going to take pictures of it. So here's what it looked like in the lab. Here's a meter stick. This is me measuring the height of the other meter stick, which we use to precariously balance a cell phone, which looked down into this cylinder, which is not a cone now, it's a cylinder down in here, and there's a dish down here that we're going to blow a bubble in, and then we've used some cheap LEDs from Amazon to make our illumination. And I'll show you a little bit more, and I'll tell you why I was measuring that and not my students in just a second. So here's a couple of measurements that we have to make, just two really. We needed to know the dish diameter, and I'll show you that in a second. We need to know the height of the camera, and then we use this figure that I show here on the right and a bunch of geometry to figure out parameters that are going to tell us about the reflected light from this bubble. So we don't really know the radius of the bubble, but if we know the height of the bubble off the bottom of the dish, and we know the diameter of the dish, then we can figure out what the radius of the bubble is. We can figure out what the angle of incidence is. And so if you do a little bit of geometry, and it does take a little bit of geometry, you can figure all this stuff out. So let's get to the fun part. So in order to measure the height of the bubble, on this figure you see, and this is a video, I'm going to show you this video in a second. I think I've got to get rid of my laser pointer here. Hold on just a minute. Okay. So in this picture, you see one of my students. This is Matthew Makasadia, and he's got a glass pipette that I stole from chemistry. And this is just a regular glass dish here. And this is another student holding up a meter stick. And then down at the bottom, you can kind of see the little cheap LED strips that we were using to illuminate the bubble. But I just wanted to show you how we blow the bubble to try to get it a uniform size in the lab. So this is a video, so you should see a video. So you see Matthew blowing, and you can see the bubble. Now we're going to turn off the lights so you can see the bubble a little bit better. So there's the bubble, and there's the meter stick. So this is how we kind of figured out what the height of the bubble is. And of course, we probably could have done this a little bit better, but we were really just kind of having fun in here. So that's how it went. And then we took images of these bubbles in a dish. And one of the cool things about this is watching the evolution of the bubble. So I have three dishes here. So top left, if you look around the edges, you see all these little swirly patterns. This is turbulence in the thin film that's forming the bubble. You see in this middle image that they go away a little bit. And then down here, you can see it sort of settled out. So this is the steady state sort of formation of the bubble that we're kind of interested in. And that's the way that we can, that's the way that we can analyze the bubble. All right, so the next step is to subtract the background. Again, we're just using a cell phone to take these images. And we used image J to take an image. This is the image with soap bubble or soap liquid in the bottom of it and no bubble. And then this is what the image looks like after we subtract this background from the images that I just showed you earlier of the bubbles. All right, so we got this far. We were able to take images, and then this happened. So we hadn't had any time to think about taking more images or anything. We shut down the university. We went on spring break, and so we were left with a few images that some groups had taken and an advanced lab that I needed to teach remotely. So this is what we did. So we started modeling. In the paper that we were using that gave sort of birth to this advanced lab experiment, we know that we can use the geometry that the author put in the paper, and if we know the wavelength of the incident light, the thickness of the film, the refraction index of the film, and the angle of incidence, then we can figure out what should be constructively interfered on reference from the film. So here's my required math for a physics talk. So we can express the total reflectance in terms of two parallel and perpendicular reflection coefficients, and then the phase angle, the phase difference between the two reflected beams from the back of the film and the front of the film is given here. I'm not going to spend much time on this because you're probably already ready for me to stop. So the thing we have to know is the RGB variation of the light source that we used. So I had to sneak back in the lab and do a spectrum of the LEDs that we used in order to come up with the ratio of red to green to blue of the light that we use as the light of incidence, or the illumination light, because we were not using a monochromatic light. So we then, as a group online, converted a MATLAB program that the author provided to a Python program. It was a little tricky because there are certain functions in MATLAB that work really well, and in Python we had to be a little bit creative, but it generates a model of the colored fringes as a function of position on the disk. So what we did was take that overall reflectance, and then we modeled it for all possible thicknesses and all possible angles of incidence, and then you come up with this color map that's shown here. So on the x-axis, it would be radial distance, and on the y-axis, it's film thickness. And then you take this color map, and then we're going to match it to our bubble image. So it's really just taking one image and matching it to this map. So for example, if I know this is the center and the edge, this color is yellow, so I go up until I see a yellow, and then I go over to the y-axis, and that'll tell me the thickness of that yellow fringe. So this worked out pretty nicely. We were able to pull out a lab even though we were not in the lab, and so I was pretty happy with it. And I still love bubbles. So this is the who cares slide. Why would anybody care about blowing bubbles and all that stuff? Well, bubbles are nothing more than thin films. And as I said in the beginning, I'm an optical spectroscopist. I do semiconductor materials. This is a picture of one of my students depositing a thin film on an ITO slide to make an organic light emitting diode device in my lab. If you think about thin films, they're everywhere. They're ubiquitous in their use in creating semiconductor optoelectronic devices. So knowing a little bit about thin films and how they act and how to model them, I think is a pretty useful skill. Now my students know how to do that. So I'm pretty excited about bubbles, and I'm still, I've got another bubble lab that I didn't show you. We did 2 of them, but okay, so this is my last slide. I just have a few remarks. Life is very short. You better be open to whatever comes at you. If I had not been open to taking a physics minor, I would not be a physicist today. You have to let go of grudges. I go over my modern physics experience. I now see that professor. He's in Texas. He's a professor here still, and I've sort of let go of that. You have to own your mistakes. When you make mistakes, you have to own it. My mistakes were often in discounting those students who did not want to get a PhD, and I don't do that anymore. You apologize when you need to. Be brave when you can, but always be humble and never stop learning and having fun. And I hope you go blow some bubbles today. So that's it.
Thank you, Toni. So if anybody has any questions, feel free to put them in the Q&A or the chat right now, and we'll answer some of your questions. Oh,
you're welcome. I have just what you're welcome. Nobody has any questions?
Oh, we have one in the chat.
Okay. Oh, I don't think I have the chat on. Can you tell me what it is, Kayla?
Yeah. So from Kyle, when you're doing outreach, mentoring, or something similar, how do you make students aware of the variety of careers they can pursue with a degree in physics that might increase interest in the major?
So I have a challenge to my students, and I tell them, if you can tell me anything you might want to do that does not involve physics, you can, it's like stump me. Just see if you can stump me. And there are very few things that you can come up with which don't benefit from physics. So I try to always connect what we're doing, even if it's, showing how liquid nitrogen freezes marshmallows and they become crumbly instead of soft and chewy. I think just having that base knowledge helps you solve problems in ways that other people can't. So that's what I try to do. I try to challenge them to name one thing that you could do that does not involve knowledge of physics. And so far, that's I have students that are just doing huge number of things: law school, doctors, one of the students I'm most proud of is a student who has a bachelor's degree in physics, and his business card says physicist. He works for Ludlam Industries, and he just does cool stuff all day long. He's just like exploring and discovering and doing stuff that I wish I was doing. He's so happy, and I'm still in touch with him. In fact, he just contacted me on Facebook the other day when I posted a picture of bubbles on my page, and he said, "I remember the bubble story." And I said, "Yeah, me too," from my qualifying exam. Max has a question about, so Max, the thickness of the film goes up to 1200 nanometers. So there's centimeters on the x-axis and nanometers. If there might have been a typo on my slide. Nanometers on the thickness, yeah. And you can set that in the Python program to go up as high as you want, but that's really that's really sort of the maximum reasonable value. So yeah, nanometers for the film thickness. And we set a minimum value of 1 nanometer, but that's just for the calculation because we don't want it to be 0. 1 nanometer is too thin. In fact, that's probably about before it breaks.
So we have a question from Anna in the chat. Thank you for a great talk. I'm wondering how you feel about the GRE and PGRE in graduate admissions. Also, do you think qualifying exams are necessary? Thank you.
Yeah, so let me just start with the physics GRE. I took the physics GRE. Remember, I had a minor in physics and I had a math degree. And so I took the physics GRE shortly after I started graduate school when I was taking leveling courses because I hadn't taken like the second semester of E&M and stuff like that. And so I did terrible. And in those days, you got negative points if you answered and it was incorrect, right? So I don't think it's that way anymore. So I only answered like 30 questions the first time I took it out of 100 because I had no idea. And so then I decided, well, that's embarrassing. And so I really studied. I finished up some classes. I took Stat Mech, for example. I hadn't had that when I took it the first time. So then I really thought, well, I'm really going to go in there. I'm going to do really well. And I answered more than double the questions. I think I answered about 75 questions the second time. And my score, which I will not say in person, would be like saying my weight in person. I would never do that. My score was probably like 10 points higher. I mean, it didn't improve. So I think it is a very, very poor measure of potential. I think it is a terrible way to think about what students might be able to do. And I think it's a really convenient way for graduate programs that have a lot of applicants to sort of just, rank order without even thinking about the real potential of the individual. So that's my take on that. Qualifying exams, I think that they're useful if they're done well. I don't think that mine was a very good measure of my potential to finish a PhD, which is what the qualifying exam, it's sort of your license. Like, you can pass all your classes and you can do really well in your research lab, but this is what really gives you the license to go for your PhD. And again, if it's not done well, if it's really just a measure of your cleverness and not a measure of your ability to solve all kinds of different problems in a creative way, then it's not really a very good way to figure out who's going to be successful in a PhD program. So I say on both accounts, it's only if there are some programs where qualifiers are tied to specific topics related to your PhD. And I think those are pretty good. And there are some schools that don't have qualifying exams at all. If you get in, they know you're good enough to do the Rice University does not have qualifying exams. So.
Thank you. We have a question from Holly. I plan on going to grad school in the fall. Do you have any words of wisdom for how to start off my journey strong?
So this fall, I can't even give you words of advice about, where
and she's going to Rice, she just said.
Oh, she is? Oh, wow. Well, first of all, look up Vanessa Espinoza. She's my student who is, she's in physical chemistry, so she's working for a chemist, but she's a physics major. And she's a terrific person. She was an associate zone counselor, she was a SPS intern and worked at NIST, met a woman who'd graduated from Rice, and that's why she's at Rice University today. So that's the first thing you should do. Look up Vanessa. She's terrific. And if you want to email me, I'll put you in touch with her. I think make sure you find some balance, but that's really hard. You just have to work hard and don't be afraid to ask for help. Find a good mentor. And I'll say that you should talk to Vanessa about the importance of finding a good research lab. It doesn't really matter if it's the most important new science on the planet and that the advisor or the mentor has all the awards in the world. What matters is being in a room with people for 8 to 10 hours a day that you like to be around and that you like to work with. And if that is not the case, then you need to make a change because you will not be successful if you're miserable. So that's my best advice for graduate school.
Thank you. We have a question from Abdul. When aiming for a job outside of physics, how can I use my physics major to benefit me in landing a job?
So that I think look at the Careers Toolbox, really read the part on how you do the knowledge and skills assessment and how you put that, how you distill that down and cast that into resume bullet points. When you write a resume, it should be for a specific job opportunity. You should not normally use the exact same resume for every job you apply for. You need to read the job ads very carefully. You need to know what they're looking for and make sure that your skill set match up with what they're looking for. If that's not the case, then maybe that's not the job for you, right? So I think the most important thing is understanding what the employer wants from an individual. And remember, when you're looking for a job, it's not about what you need from the job. It's about what the employer needs from you. What do you have that they want? And then emphasizing that in a way that gets you the interview on your resume. I think that's the key.
I can also advocate for Careers Toolbox. We used it when I was a senior in college, and it was very helpful.
Yay.
We have a question from Evangeline. Hi, Toni. Thank you for a great talk. Do you have any tips for students who suffer from severe exam anxiety?
Yeah, I was one of them. I was not really very good at tests. And finally, I just said, okay, you know, you figure out what works for you. For me, I had to just, I always tell my students, and my students who know that, they'll laugh. When you walk into a test, it's like walking into an arena, fighting a bear, and all you've got is a sharp pencil, right? You have to go in. For me, it was sort of anger driven, like, I am not going to let this test get the best of me. I think that it's easy to go into a test, and if you just feel the least bit underprepared, you just let it dominate your thoughts. So one of the things I do on a test is I write down every thought that I have in my head. Because sometimes when you think it out, that's what physics teaches us, right? How to think it out. Sometimes if you write things down as you're thinking, then you think of other stuff that you know, and then you go, oh yeah, and then you go back and you can do better. And I can say that for me, when I grade tests, I want to know if you think you're not doing it right, you should write that down. Like, I have given people full credit on exams when they go, look, I did all this, I got this result, I am sure that this is not the right result because it should be smaller or bigger or whatever. That in itself tells me that you're a critical problem solver, even if you screwed up the math. So I think, first of all, don't be so hard on yourself. Try to focus on the things you know. And if you're not sure about stuff, then you should ask somebody. Don't ever be thinking that people are going to think you're too dumb or something like that.
Thank you. So we have 3 more questions in the chat, and I think after that we'll be good. So from Maria, thank you so much. What would your advice be for someone applying to a job or program with a weak area on their resume or CV?
Well, so if you know you're weak in an area, I would try to build up that strength if you think it's important. One of the things that you might be referring to, I'm not sure, is computational skills. Really important right now. And if you don't have some expertise in that area, take an online course or even just a self-paced free course on Python or programming or coding or something like that. So I would say focus on your best skills and make sure you're matching your best skills with the skills that an employer wants. If you're applying for a job where the #1 thing they list is proficiency in coding, and you're not a coder, then don't apply for the job because you're probably not going to be a competitive candidate for that job.
Thank you. From Abigail, do you have any advice on overcoming people who judge you solely based on you being a woman?
Make an A in the modern lab. That's what it did. That was for me. That was it, right? I was judged not based on anything other than that I was a woman who was likely not to do well in the lab. And for me, that was just a challenge. I was not going to let that stop me. And if that's what they're going to do, then they're going to do it. And there's probably not much that you're going to be able to do to change their minds. When I was a young student, there were several just inspirational women who had persisted through, things that I can't even imagine. One of my biggest heroes is Mildred Dresselhaus, who is no longer with us, but I got the opportunity to meet her and then get some advice from her when she won the Orsted Medal at an AAPT meeting, and my students met her. I mean, if you're worried about being the only woman or people judging you because of you're a woman, you're gonna just have to let that go. And just be who you are. You can't be apologetic for it. You just have to keep doing what you love to do. And you're gonna meet people. I had a couple of experiences in graduate school where I ended up making a B in a class I should have made an A in, and I know I did. I know it had something to do with my gender. So I think you just have to persist to do what you want to do. I wish it was better now. I wish that we didn't have this conversation still. I'm too old to be having that conversation, and it just pains me that we still have to have it.
Agreed. And then our last question from Anna. How do you see higher education in physics working towards diversity, inclusion, and equity in the future?
Whew, that's a big question.
The big last question.
Yeah. So I think that if we don't, we lose. We all lose. I've been on a diversity committee for a really long time of one kind or another. And it was years ago, I was working on the SPS National Council. We were on a diversity committee. I was working with Willie Rockwood, who used to be the department chair at Morehouse College, and now he's in physics at West Virginia. He may be the chair, I don't know. But we decided that one of the things we have to really embrace and realize is that the more diverse the problem solvers at the table, the better the problem gets solved. And this is always true. I've never had an idea, even when I'm teaching, that I don't bring to the class that they don't make it better, right? Because they're different. They have different ideas and different backgrounds and so on. So I think valuing diversity is one thing. And I think we are there. We do, but we then have to support that with inclusion and equity. And that's really the hard part. I think that many of my colleagues in physics work very hard to do things that work toward equity and inclusion, and yet in so many ways we're failing. I'm hoping that this current atmosphere really does change the way we think, and make us all more self-reflective about our own part in what's happening. I have to face as an individual, and I think all of my higher ed colleagues have to face our own biases. We have to learn what we have in us that affects the way we bring out what is in students, and the way we judge what is in students, and the way we gauge their potential. All of us come from a place of our own culture. We can't separate that. And so I think if we don't make some changes, if we don't look at things like stop using the physics GRE as a way to gauge whether somebody can get a physics PhD or not, then we lose. We lose as a society, we lose as a community, we lose as a discipline. So I think there's a critical mass of people that have to know that and just keep saying it and saying it and saying it until everybody kind of signs on. So that's probably not a very good answer. I can tell you that I have I'm very concerned and passionate about this, and I hope that I can generate that same kind of passion and concern in my colleagues and friends.
Thank you, Toni. I think that was a wonderful answer. Thank you again, Dr. Sauncy. Thank you to everybody for your awesome questions. We really appreciate it. And thank you for joining us. Have a nice rest of your day, and we'll see you at our next talk.